how hectic your it doesn't matter how hectic your day was. You can't help admiring the beauty of this evening. I hope you are having a good time right now. Good evening. I'm absolutely delighted to welcome you all for the third day of national level workshop on recent trends in fuzzy inventory models, modular lattice, and differential calculus and its application. Organized by the Internal Quality Assurance Cell IQAC and Department of Mathematics, Shri Krishnaswamy College for Women. Mathematics may not teach us how to add happiness or how to minus sadness, but it does teach one important thing. Every problem has a solution. Once again, I welcome you all for the third day of national level workshop on differential calculus and its application by Dr. S. Nalini ma'am, Assistant Professor and Head Department of Mathematics, Arulmigu Arthanareeswarar College of Arts and Science, Tiruchengode. I am Hariyara Priya, Department of Mathematics. I have the privilege of being your host for this program. Now, I would like to invite Dr. R. Esther Felicia ma'am, Head Department of Mathematics, to present the welcome address.
Good evening to one and all present here. It gives me an immense pleasure to extend a warm welcome to the Chairman and Management Trustees, Krishnaswamy Educational Trust, our Dean, Dr. R. Revati ma'am, Principal, Dr. Anita Rajendran ma'am, and the Internal Quality Assurance Cell. I extend a pleasant welcome to our eminent guest of honor, Dr. S. Nalini ma'am, Assistant Professor and Head, Department of Mathematics, Arulmigu Arthanareeswarar Arts and Science College, Tiruchengode, for this 3 days national level workshop on recent trends in fuzzy inventory models, zero supermodular lattice, and differential calculators and its applications. Welcome you, ma'am. We are happy to have you as a resource person for today's session on differential calculus and its applications. I welcome all the participants from various institutions who seek to enlighten themselves from this valuable session. Thank you.
Thank you, ma'am. Now, I would like to invite Mrs. M. Tamilarasi ma'am to give the brief introduction of our chief guest.
Good evening to all. It gives me an immense pleasure to start this auspicious occasion by heartily welcoming our chief guest, Dr. S. Nalini ma'am. Our chief guest, Dr. S. Nalini, MSc, MPhil, SET, PhD. She had completed her PhD in Bardia University in the year 2020. She also qualified Tamil Nadu SET in the year 2016. She have a research interest in differential equations and difference equations. She is having 16 years of teaching experience as assistant professor and also the head of the department. Currently working as an assistant professor and head of department mathematics in Arulmigu Arthanareeswarar College of Arts and Science, Tiruchengode. She had finished 8 online courses in NPTEL. She served as one of the reviewer in American Journal of Applied Mathematics and also Journal Mathematics and Statistics. She served as a chief guest and keynote speaker in national seminar at Sri Sarda Nikitan College of Science for Women, Karur. She had published 9 research papers in international and national journals and also 8 papers presented in the conference. She had participated in more than 43 seminars, symposiums, workshops, and etc. She had successfully completed 10 research academic modules. She participated in the online quiz also. She got appreciation certificate for meritorious service contributed to the institution NSIT in the year 2013. She got a reward for an effort to produce 100% result in the Anna University examination held during the academic year 2011 to 2012, semester 4 in the Statistics and Numerical Method, subject at Narasu Sarthi Institute of Technology, Salem. Thank you. Welcome you, ma'am. Thank you.
Thank you, ma'am. Now, I would like to invite Ms. Nalini ma'am, Assistant Professor, Head Department of Mathematics, to take over the section.
Thank you, ma'am. Thank you for your introduction. Ma'am, How to share my PPT, ma'am? Yes. Okay, happy evening to one and all present here. First, I thank Almighty God for giving this opportunity. Next, I thank and say evening wishes to Management Director, Dean, Principal, HOD and faculties of Mathematics Department of Shri Krishnaswamy College for Women, Chennai. Mathematics is not about numbers or equations, computations or algorithms. It is about understanding. It is a part of our life. Some changes give you happiness and some changes give you unhappiness. If you are able to predict the rate of change, then you only are the happiest person in the world. Yes, today we are going to learn about rate of changes and its real life applications. So this lecture begins with introduction of calculus. Next we are going to see some history of calculus and its types. Following this, briefly I explain about differential calculus, that is definition of differential calculus and its real life applications. Finally, I give some research topics in differential calculus. So calculus. You know the universe is constantly in motion. Stars, planets, and galaxies are constantly changing. Calculus is a branch of math that calculates how matter, particles, and heavenly bodies actually move. Calculus is a Latin word which means stone or small pebbles. Romans used stones for the counting of infinitely small numbers. Mathematicians began using the same term and the name instead. Actually, it is called infinitesimal calculus. Calculus is actually called infinitesimal calculus, which means changes over very small intervals of time. Calculus is used to calculate the rate of change in real time. So it is language of engineers, scientists and economists. The work of these professionals has a huge impact of our daily life, from your microwaves, cell phones, TV and car to medicine, economy and national defense. It's the father of calculus. So the discovery of calculus is often endorsed to two important men. First one is Isaac Newton and Gottfried Leibniz. Both are independently developed its foundations, although they both were instrumental in its creation. They thought of the fundamental concepts in very different ways. While Newton considered variables are changing with time, Leibniz thought of the variables x and y as ranging over sequences of infinitely close values. He introduced dx and dy as differences between successive values of these sequences. Leibniz knew that dy by dx gives the tangent, that is the slope, but he did not use it as a definite property. On the other hand, Newton used quantities x dash and y dash, which were finite velocities, to compute the tangent. Of course, neither Leibniz nor Newton thought in terms of functions, but both always thought in terms of graphs. For Newton, the calculus was geometrical, while Leibniz took it forward towards analysis. It is interesting to note that Leibniz was very conscious of the importance of good notation and put a lot of thought into the symbols he used. Newton, on the other hand, wrote more for himself than anyone else. Consequently, he tended to use whatever notation he thought of on that day. This turned out to be important in later developments. Leibniz's notations was better situated to generalizing calculus to multiple variables, and in addition it highlighted the operator aspect of the derivative and integral. As a result, Much of the notation that is used in calculus today is due to Leibniz only. The development of calculus can roughly be described along a timeline which goes through three periods. First one is anticipation, the next is development, and third one is regularization. In the anticipation stage, techniques were being used by mathematicians that involve infinite process to find areas under curves or maximize certain quantities. The development stage, Newton and Leibniz created the foundation of calculus and brought all of these techniques together under the umbrella of the derivatives and integral. However, the methods were not always logically sound. It took mathematicians a long time during a regularization stage to justify them and put calculations on a sound mathematical foundations. In the development of the calculus, both Newton and Leibniz used infinitesimals, quantities that are infinitely small and not non-zero. Of course, such infinitesimals do not really exist, but Newton and Leibniz found it convenient to use these quantities in the computations and the derivations of results. Although one could not argue with the success of calculus, this concept of infinitesimals bothered mathematicians. Lord Bishop Berkeley made a serious criticism of the calculus, referring to infinitesimal as the ghost of deported quantities. Berkeley's criticisms were well founded and important in that they focused the attention of mathematicians on a logical clarification of the calculus. It was to be over 100 years. However, before calculus was to be made rigorous, ultimately Cauchy, Weierstrass, and Riemann reformulated calculus in terms of limits rather than infinitesimals. Thus, the need for these infinitely small quantities was removed and replaced by an idea of quantities being close to others. The derivatives and the integral were both reformulated terms of limits. When we first studied calculus, we often learn its concept in an order that is somewhat backwards to its development. So calculus is generally classified into two types. First one is differential calculus and another one is integral calculus. So differential calculus means if you cut something into small pieces to find how it changes. That is called differential calculus. So integral calculus means you join the small pieces together to find how much there is. This is the difference between the differential calculus and the integral calculus. The study of calculus usually begins with the basic definition of derivatives. Because the differentiation is a method of computing a derivative, which is the rate of change of the output y of the function with respect to the change of the variable x. So derivative means the rate of change. The differentiation means computing the derivatives. Derivative refers to the rate of change of y with respect to x, and this relationship is expressed as y is equal to f of x, that is the function of x, which means y is a function of x. Derivative of the function f of x is defined as the function whose value generates the slope of f of x, where it is defined and f of x is differentiable. It refers to the slope of the graph at a given point. Differentials are represented as dx, dy or dt. Dx means small changes in x and dy means small changes in y and dt means small changes in t. When compared changes in related quantities where y is a function of x, the differential dy can be written as dy is equal to f dash of x into dx. That means the small changes of y is represented as the function, the derivative of f of x into the small changes in x. The derivative of a function is the slope of the function at any point and is written as d by dx. Here I simply explain the derivatives. That is, if you consider this potato as f of x and the cutter this potato is called as the first derivative. This is the first change. And the next change is fried potatoes, that is chips. That is the second derivative. This is for simple example for differentiation. That is derivatives. So the differential calculus is mainly classified into two parts based on the independent variables. So first one is ordinary differentiation and the next one is partial differentiation. If you have only one variable, if you differentiate with respect to only one variable means that is ordinary differentiation. If more than one variable means it is called partial differentiation. So partially differentiate a variable function. So the differentiation of a function of two more variables when each of these variables receives an increment is called total differentiation. The two major applications of differential calculus is modeling phenomena and solving equations. Now we are going to see how to create mathematical modeling. Here I give two examples. The first one is, suppose you consider this street, intersected street. So in the one end of the street is a car is there and another one is a bike is there. Suppose this car moving the intersection towards the intersection about 60 miles per hour and the bike is 30 miles per hour. The distance between the car and this intersection is 0.8 miles and the bike and this intersection is 0.6 miles. Now, first you find what is the distance between the car and the bike. So we consider here the distance between the car and the bike is s, and the distance between the car and the intersection is x, and the distance between the car and the intersection is y. So now it's form a right angle triangle. This right angle triangle you have to find s first. So here what we have find out means the change of this distance with respect to the time. Okay. So first we formulate this distance s. So here we use the Pythagoras theorem. So we know the Pythagoras theorem. So the x squared plus y squared is equal to s squared. Here we know that x and y values. Here the distance between the bike and the intersection, that is x, is 0.6, and the distance between car and the intersection is 0.8. So 0.6 the whole square plus 0.8 the whole square equal to s squared. So after computing this, you get s is equal to 1. So now you know the changes of this car. This car is moved to intersection. Okay, so the changing y is 60 miles. The car moving 60 miles per hour. So here changes of dy by dt. That is this y. Y is the car moving. So the distance is reduced. That's why here we use negative minus 60 miles per hour. That is dy by dt. And then this bike is moving towards this intersection. Here the distance also, here also the distance decreased. So here the changing of this x with respect to the time is minus 30 miles per hour. Here the distance are reduced, so that's why here we use the negative. So minus 30, dx by dt is minus 30 miles per hour and dy by dt is minus 60 miles per hour. So x square plus y square, we know that distance x square plus y square equal to s square. If you differentiate this, you get 2x into dx by dt plus 2y into dy by dt equal to 2s into dvs by dt. And we divided by 2, so you get x into dx by dt plus y into dy by dt equal to s into ds by dt. So actually here we find the distance changes only. So here we substitute, we know x, y, dx by dt and dy by dt. So x into dx by dt plus y into dy by dt equal to s into ds by dt. We substitute the values 0.6 into minus 30 plus 0.8 into minus 60. For my s value 1, the previous slide here you have s value is 1. So 1 into ds by dt. So ds by dt equal to, after computing this, you get minus 66 miles per hour. So the distance right over here is changing 60 miles per hour. Okay. So next, so now we are going to see modeling population growth where the population being studied also undergoes harvesting. So this is our next mathematical modeling example. Now you imagine a fisherman he catching some amount of the fish population in each year. To start with, there are a certain number of fishermen involved who each year catch roughly a constant amount of fish. Should we allow more fishermen, perhaps equipped with sophisticated fishing technology, to join the hunt? No, because to avoid the danger of overfishing, we could allow a small number of additional fishermen to join in. We expect that such a change would increase the catch by a relatively small amount and hence decrease by a similarly moderate amount to the level of fish remaining in the river. Mathematically, one can model population growth by the harvesting via a differential equation of the form. That is, d of f of t divided by dt is equal to g into f of t into 1 minus f of t divided by c minus rho. Here f of t is mentioned as population and g is the growth rate of the fish. C is carrying capacity and rho is the harvesting level. The solutions of this equation for various harvesting levels shows the existence of a critical fishing level. Technically, it is called the bifurcation value. If the fishing level is increased beyond this critical value, even every slightly, then the model predicts that there will be a drastic crash in the fish population, potentially leading to extinction or near extinction. Okay, these two are just a mathematical how to mathematically model this differentiation. So next we move to some real life applications. So in the engineering, we use the derivatives to determine the maximum and minimum values of particular functions. Derivatives are met in many engineering and scientific problems, especially when modeling the behavior of moving objects. In electrical engineering, they are used for finding moments and current flow. How much of current is flowing the wire. Differentiation provides different forms of information. Example, for mechanical engineering and aerospace engineering, the derivative of distance with respect to time, dx by dt is called velocity. The derivative of velocity with respect to time, that is the second derivative. Differentiation of the velocity is called as acceleration. And the derivation of this acceleration with respect to time, that is the third derivative. This third derivative is called jet. So each engineering specialty has its own equivalents for these equations. So in robotics engineering, differentiation is used for motion and control of robotics. Mobile robots drive found around with a velocity and an acceleration. So robotics arms moves each joint has angular velocity and acceleration. A differential equation is often used as a description of how some type of system will change over the time. It says if the system is in some state right now, then this is how much the state will change by. For example, if you are on a roller coaster going down a hill, your current state might be described by how fast you are moving. That is, the moving is the velocity, and how far down the hill you are. At the point in time, you can use a differential equation to describe how much your speed position will change over the next instant of time. Let's say now this roller coaster has brakes and you don't want to move too fast. You need to control your speed. So you can look at your current state and use that to calculate how much to apply the brakes to make sure you stay at a constant speed. Perhaps you want to move at some speed back up the hill, well, you can calculate how much power to apply make it happen. You can actually do this with a ton of different systems. How do you think a Segway stays upright? How does your journey control make sure you keep going on the highway? The answer is controls. And it's all based on calculus. This is also how make a robot move where you want it to, or pick up something where you want it to. So calculus is used basically anywhere engineers and scientists work. So here given one more example for aerospace engineering. Differential calculus tells is calculating the ideal rocket equation for calculus application. This is beneficial in rocket analysis and gravitational modeling over space and time. Most physics models use calculus, especially in astronomy and complex systems. So next one is the optimization. How the calculus is applied in the optimization. Calculus is used basically. Even sociologists might use calculus to examine how ideas spread across populations or how cultures change over time. Many fields can take advantages of machine learning to optimization techniques that are based on calculus. Calculus is often used to perform the optimization. If you want to know when a peak or valley in a set of data occurs, find where the derivative is 0. If the derivative is 0, you can identify the peak or the valley. It really in one of the most valuable forms of the mathematics. So even the credit card companies also use the calculus to set the minimum payments due on the credit card statement at the exact time the statement is processed. So in economics, also use the calculus, use the compute the marginal cost and the marginal revenue, enabling economics to predict maximum profit in a specific setting. So here I will give one example. There is marginal rate of substitution. How they calculate marginal rate of substitution. So marginal rate of substitution means the amount of good that a customer is willing to consume compared to another good, as long as the new good is equally satisfying. So the original rate of substitution, the formula is ds negative dy by dx. So it will give a good result. Yeah, calculus not only for engineer, not only for scientist, not only for economics, medicine. In medicine also they used calculus. The equation for each drug looks unique depending on its properties and the patient's anatomy. Calculus is necessary for medical professionals to have the ability to map the relationship between drug concentrations in the function of patient's disease drug concentration in the body over time. The first derivative, that is the slope of the given point, the first derivative of the mathematical function of a patient's disease course is the rate at which a patient is moving from wellness to death. So first derivative means how the patient is moving from wellness to death. On a patient's illness course, the second derivative is essentially the rate at which a patient is moving more or less sick. The calculus is used to in medicine to measure the blood flow, cardiac output, tumor growth, and the determination of population genetics, among many other applications in both biology and medicine. So medical professionals apply calculus in pharmacology in order to determine the proper dosage. So next, neurology. This differential calculus is used for calculating change of voltage in a neuron with respect to time. But integral calculus is used to compute the voltage of a neuron at a certain point. So here in the neurology also the calculus is used, differential and both in differential and integral calculus are used. So you may be surprised to know that the use of calculus is not restricted to engineering or medical science, but can also apply to music. Some applications include harmonics and oscillation created by a damped harmonic is not infinite, as friction and air resistance will dissipate the energy. Calculus is used to anticipate these motions to make the proper adjustments and provide the best musical experience to the listeners. And the acoustics. Resonance and forced oscillation can be computed using calculus. Air resistance varies at different frequencies and resonates throughout an enclosed space. Whenever a musical instrument is played through calculus, we can make improvement on acoustic and improve the listener's experience. Generally, we hear the music sounds in a wave form. These waves are converted into equations. When we change this equation, we will get an interesting music. So here I give one example. The simplest model of a musical sound is a sine wave. Here we take the x-axis, we take time, and the y-axis, we take pressure. The pressure equation is P is equal to A into sine of F T into 2 pi. The P is means pressure in pascals, and T is time in seconds, and A is amplitude, that is the height of the wave, and F is frequency or pitch, and T is period of second. That is T is mentioned as 1 by the frequency, 1 by F. If we change the pressure, if you change the pressure with respect to time, so you get a music. That is here we differentiate the pressure with respect to the time, and the time interval is 0.15. So you get A into F 2 pi into cos of F 2 pi into 0.15. If it changes in derivatives, it gives interstate music. And derivatives of a tensor curve, the effective velocity. So the differential calculus are applied in many areas, not only in the engineering, not only in the physics, not only in the scientists, applied in all the areas. In our daily life, we used the calculus. So here I give only very few examples to only here I give. Here I give some resource topics. That is ordinary and partial differential equations, differential differential equations, delay differential equations, neutral delay differential equations, fractional differential equations, algebraic differential equations, integral differential equations, complex differential equations, functional differential equations, numerical methods for differential equations, oscillatory criteria and stability theory, random and stochastic differential equations, and mathematical modeling in different differential equations. So the application of the differential calculus is mostly involved in the differential equations. Via the differential equation. The solution of this differential equations give the results are they give many values. So in mathematical models, for real valued programs, the classical idea of ordinary differential with integer order have been applied to show dynamical behavior in systems, biology such as enzymatic reaction models, population growth models, and cell signaling pathway models also. If you have any queries or doubts, you can ask me.
Participants, kindly post your queries in the chat box. Are you here, Priya?
Yes, ma'am.
You can start now.
Now, the next few minutes will be a question section. Participant can ask the questions.
Arigara Priya, you can call for vote of thanks, ma'am.
Okay, ma'am. Now, I would like to invite Dr. S. Subbulakshmi ma'am to deliver the vote of thanks.
So, a very warm good evening to all. Being thankful and expressing our gratitude to all the people who had been instrumental in the successful outcome of the event is an essential aspect of every program. I, Dr. S. Subbulakshmi, deemed it as a great honor and privilege to propose the vote of thanks on this memorable occasion. First of all, I start by giving glory and thanks to the Almighty God for making today's occasion a resounding success. I would also like to thank him for helping us with good connectivity, which is a need of the heart to make any great session a great success in today's pandemic time. We are deeply indebted to express our sincere gratitude to the resource person, Dr. S. Nalini ma'am, Assistant Professor and Head, uh, Arulmigu Arthanareeswarar College of Arts and Science, for kindly accepting our invitation in spite of his hectic schedule and gracing the session with thought provoking address. Thank you so much, ma'am, for this insightful session. We are extremely thankful to our chairman and educational trustee of Krishnaswamy Educational Trust for their constant support and able guidance. I would also like to express my profound gratitude to Shri K.B.K. Rajmohan sir, Shri K.B. Arun sir, and Shri K.B. Krishnanand sir for their meticulous support and throughout the year for various programs. Our heartfelt thanks to Dr. Anita Rajendran ma'am, Principal, Sri Krishnaswamy College, and Dr. Revati ma'am, Dean, Sri Krishnaswamy College, for all their support and stewardship that they extend to the organization on the whole. I would like to extend my heartfelt gratitude to Dr. J. Radha, IKC Coordinator and Head, PG Department of Commerce, and Dr. Esther Felicia, Head, Department of Mathematics, Sri Krishnaswamy College, for their unstinted support and guidance throughout the organization of this 3 days national level workshop. I thank all the faculty members of the Department of Mathematics, Sri Krishnaswamy College, for their cooperation and hard work in the organization of this workshop. I would also thank Harihara Priya, student from the Department of Mathematics, for hosting the entire event with a great cheer. I thank all the audience for accepting our invitation and being here today to grace the occasion with their presence. Thank you, one and all. Thank you.
Thank you, ma'am. Thanks for all the participants for the 3D national workshop for your participation. Thank you. We can end up this session. Thank you, ma'am.
Thank you.
Thank you so much, ma'am.